Hello everyone, welcome to ResearchHUB again. So in this lecture, we are going to do confirmatory factor analysis, or here in the case of partial least squares structural equation modeling, what we call confirmatory composite analysis. Okay, so because the PLS-SEM algorithm, it uses the composite structures of the latent variables. That's why we call it confirmatory composite analysis, CCA, instead of CFA. For the normal structural equation modeling, the covariance-based structural equation modeling, we would call it CFA, confirmatory factor analysis, right? So in the previous video, I have shown you how you can build a measurement model like this, okay? So here, we already put the path estimation, we already put the path links, which variable with latent variable will affect which ones. So we already put them here, right? But we will first still estimate a factor model, and then we will later do a composite, we will later do a path model, the main PLS-SEM model, okay? So in this video, the focus will be on the factor model. And here also one more thing you should note down is that here you see the arrow from the latent variable to the arrow goes from the latent variable to the observed variable, okay? And this indicates that we form them as a reflective factors, okay? Reflective latent variables, okay? For formative latent variables, the arrow would go from the observed variable to the latent variable, the opposite direction than what we have here, okay? So in later videos, I will also show you how to do estimation of a formative model. But for now, let's go with this reflective model setup, okay? So we have our data, which active here, the green one here, that indicates that this is the active data set. And here we have set up the measurement model. Now we are simply going to estimate it. And to estimate, we are going to go here on calculate, and we go to PLS algorithm. Okay. So we click here and we see these options. And here we will select factor. Okay. And here you can change the maximum iterations, or you can also go with the same number. It's okay. These are the default settings. And the great thing about this software is that you can read about what they mean here, okay? So each of the options, what they really mean, you can read about them here. It's really great, okay? But here, what we're going to do now is we are simply going with the factor model. Okay, so we're just going to click start calculation, and it will start our estimation. And the estimation has been done. Fantastic, okay. So now to see the results here, you can click here on the report, it will open it. You can also click it and export it into Excel. You can open it also in HTML format. You can also open it in an R format. And if you want to remove your results, you can just click here on the remove. But now I want to see the results, right? So I'll just click here on the report. And here you can see the results. So here you see, this is our canvas, this is our data, and this is our first estimated result for the factor model, okay? So now, what are we really interested in here? Here we are interested in the factor loadings. And to see that, we click here on the outer loadings, okay? So for factor loadings, the threshold we follow is that it should be greater than 0.708, right? And in this case, you see all of them are higher. All of them are higher, all of them are higher. And that's why they're green. This is also cool about this software. When it is not higher than this value, it will not show it in green. So let's have a look here. For example, here, it is just below 0.708 and it shows red, right? So only one of them is red and all others are in green. But we had a couple more, like one or two more in red, which we removed. For example, the BD, it was the BT, I think. It was the BT3, yeah, that was much lower than 0.708, I think. And then we removed it. But this one is almost 0.7, so that's why we keep it, right? So these are the factor loadings that you would normally report in the measurement model part of your study. Okay, and now if for any reason you would like to see your latent variables, then you can click here on the latent variable, and here you will find the scores of the latent variable, okay, for each of the respondents. And here we have 272 respondents, right? So for each of them, based on the estimation, based on the composite factor analysis, we have our latent variable scores estimated. Okay, so these are the scores. If you want to see the latent variable correlation, here you have it. Here you see on the diagonal, we have the 1 because the factor with itself will have correlation of 1. And below the diagonal, we have the correlations, but below and above are the same values. For example, here, this cell is the correlation between bus tangible. So if I use my markers here a little bit. So this value here, this is the correlation between bus tangible and bus drivers, bus tangible and bus drivers. And here also you see this value is the same. It is also the correlation between bus driver and bus tangible. So the value is same. Okay. So on the here you see this is the value between life satisfaction, correlation value between life satisfaction and bus driver. Here also the value between life satisfaction and bus driver. So above and below the diagonal, we actually have the same value. So normally when we report it in a paper, we only report the lower part of the diagonal and not the upper part of the diagonal, right? So that's something you can get from here. Okay. And if you need the latent variable descriptives, actually you also can have that from here, right? And another cool thing is if you want to copy it to Excel for your reference, you can just click here Excel format and you just open an Excel file, which I normally do actually. Whenever I'm doing some analysis for a project, I just open multiple Excel sheets and I save all the results there. So for example, here I have my latent variable descriptive. So maybe you will give a name here, you will call it LTDES descriptives, right? If you want to have the correlations, so you will just click on the latent variable correlation, click here Excel format, and then you will open a new Excel sheet, paste it here. You can call it LT core, right? Looks nice, right? If you want to, so another thing, the main thing you want to have from this factor model is the outer loadings, this part. So just click here on Excel format and save it here in another sheet. Okay, so here you are going to call it loadings, FL factor loadings, right? So normally for the measurement model, we report the factor loadings and then we report the validity and reliability statistics, right? So for reporting validity and reliability, we have to come here. Construct reliability and validity. Here we have Cronbach alpha, row A, composite reliability, and average variance extracted, AVE. So all these things we normally report. Okay. And here, just to give you the threshold, once again, I should maybe clean my window here. Yeah. So the value of Cronbach alpha, row, and composite reliability, the value of these ones should be higher than, greater than 0.70. Okay. And the value of average variance extracted, these values should be higher than 0.50. Okay. So these are the thresholds, and I will provide some links of the studies that you should refer to when you refer to these values. I will put the links below in the videos. Okay. So here you see all of these values meet these thresholds, right? That means our latent variables are reliable. Okay. So from the Cronbach alpha, row A, and composite reliability, we can say that our the values here, they are reliable. Okay, so that's a great thing. And normally if you want to say it actually kind of indicates reliability. And another concept is the convergent validity. Okay, so for convergent validity, it would mean that if the items are measuring the construct, if they're measuring something that is valid construct. Okay, so to see that, actually here I should maybe clarify a little bit more. So we have the concept of reliability. And then we have the concept of validity. So for validity, we again have two concepts: convergent validity and we have divergent validity or discriminant validity. Okay, both these two, there are two. So normally, what does reliability mean? Actually, for this, I can to explain reliability and validity, I can quickly show you a figure which will make it clear. So here, this figure actually can explain the concept of validity and reliability nicely. Okay, so here, if you look here, we have reliable and not reliable, and then here we have not valid and valid. Okay, so here, let's say we have 5 questions to measure a latent variable. Okay, and the cross here is the average score of these 5 measurement items. Okay, when the average score is equal to the true score, that would mean the concept is valid. Okay, so we don't know the true score, but for presentation here, let's assume that the true score is in the bullseye. Okay, so when the cross, the average of the items measured, okay, the items that measure the latent variable, the average score of that will be on the bullseye here on the center, then we will say it is a valid. So we are measuring what we are supposed to measure. Okay, and the concept of reliability is that the items, they measure something in a reliable way. So for example, here, if you look here, all the items, they are closer, right? They measure something. For example, here, it is not valid. So they are not measuring what we are supposed to measure, but they are still measuring something. Our 5 questions, they are still measuring something. And here, if you look here, in this case, it is not reliable, not valid. You see the questions, the score of the items, they are dispersed, and the average from the average, they are very dispersed. Okay, and the average is also far from the bullseye. So here, when the average, the cross here, when it's not in the center, that would mean it's not valid. And when the questions are dispersed from the average, it means they're not measuring something reliably. Okay, so here this situation is not valid and not reliable. But this is the situation we want. Okay, all our questions, they're measuring something and then measuring what they were supposed to measure. So what they're supposed to measure, that's validity, and they're measuring something in a way, in a satisfactory way. So that's the reliability. Okay, and this valid but not reliable, this situation cannot actually exist. That's why we have empty box here. Okay, so for the measurement model and latent variable perspective, so the reliability and validity would mean that when the items are measuring something properly, they were supposed to measure, let's say, customer satisfaction, and they're measuring customer satisfaction. So that's one we would call it valid. And how well they are measuring the customer satisfaction, that's what we will call reliable. Okay, so that would be the concept in the context of our structural equation modeling. So now here, what I was saying is that, okay, so we have reliability, and reliability, we can measure it from these 3 measures. Okay, if they are higher than 0.70, then we can say that our latent variables are reliable. Okay, and for validity, we have convergent validity. So for convergent validity, there could be 2 things that we can look into. One is that the significance of the statistical significance of items, and another one is the AVE, which should be greater than, it should be greater than 0.50. Okay, so both of them together would indicate convergent validity. And for divergent validity, we have 2 approaches that we can use. One is called the Fornell-Lakers test. For now, if I just write FL, okay, FL test, and another one is the HTMT test. Okay, so these are the two things we can do. So now let's actually have a look, how can we do that? Okay, for average variance extracted, we can see it from here already. All the values are in green, all of them are higher than 0.50. Fantastic. For significance of the items, we actually have to estimate a path model to see the p values. Okay, so we will see it in the path model estimation part. Okay, and for divergent validity, we have the Fornell-Lurker criterion test. So for that, we can click here, discriminant validity. Here you see Fornell-Lurker criterion, and here I'm going to again write a little bit here. So here you see these values below the diagonal. Okay, these values are actually our, below the diagonal, these values are our correlation values. Okay, they are same as our correlation values. Okay, and here you see these values are the square root of our average variance extracted. So if you remember, if you come here, you see for bus driver, the average variance is 0.698. Okay, so if I take the square root of that, just if I create another Excel sheet here, SQRT, if I just take the square root of that, 0.698, you see I get 8354, right? So if I come here and discriminant validity, you see 835. Okay, so here on the diagonal, all the values are the square root of the average variance extracted. So I'm going to write it for you. Here, these values are actually square root of AVE. Okay, so here the idea is that all the correlations should be less than. Okay, so all the correlations should be less than a square root of AVE. If that is the case, then we actually establish divergent validity, and this approach is called Fornell-Lurker criterion. Here it means that the average variance explained by that variable itself should be higher than what can be explained by the correlation of this variable with another variable. Okay, so that's the idea. So the variable should have higher explanatory power with itself, okay, than what it shares with other variables. Okay, so that's the idea here. And one more criteria we have here is heterotrite monotrite. It's a bit long name. Heterotrite monotrite ratio, HTMT. Okay, so here actually now we have too many things here. Maybe I will clean up a little bit to make it a bit easier for us to see. Okay, so here normally the values, the threshold values here, if the values are less than 0.85, that's good. Okay, that's good. Normally if they're less than 0.8, that's very good, and if they're higher than 0.9, then it's kind of cautionary. Okay, it could be problematic. The idea of divergent variable is that each of the latent variables are different from other latent variables. Okay, so that's the idea. That's the idea here. Bus driver as bus tangible are two different variables. They are not the same thing. Okay, if they were the same thing, why would we use two variables in the same model? Okay, so here the idea is that the idea of divergent validity is that the variables, the latent variables, they are different from other latent variables. Okay, so normally, as you can see, all the values are lower than 0.85. We have all the green values. So you can just copy this table and report it in your paper. So I will just copy it in Excel format. And here, let's say if I just remove this value here, I'm going to paste it here. And this one is HTMT. So these days it has become norm to report actually both HTMT and Fornell-Lurker criterion, both of them. Okay. It should be test, not text. Okay, so I'm just going to copy this one as well. Okay, great. Right, So this is how we can actually report a measurement model, and we can show that, okay, the measurement model is reliable and valid, and we can proceed with the PLS-SEM estimation of the model. But here in the reporting, you see there are some other statistics that you would like to check. For example, the model fit. Here, normally the model fits for the PLS-SEM is not really well established yet. Okay, but some of these estimations you can report them. So normally the SRMR value below 0.08 is normally okay, and the NFI values, normally when these values are higher than 0.8, they are okay. Okay, so but the model fit of the PLS-SEM are not well established at the moment, but normally when they are reliable and they are valid and the factor loadings are good, then it's good to go. So in the next video, I'm going to show you the estimation of the same model, but in the PLS-SEM, the structural equation model instead of the factor model, and how to report that and how to interpret that. Okay, so that's what I'm going to show you in the next video. Thank you.